morning, everyone. The paper we will discuss today is overview of the SPARC physics, basis towards the exploration of burning plasma regimes in high-field compact tokamaks. If you have any questions, I'd be happy to hear your comments. Section 5. Plasma-facing components and heat flux heating. The compact size, high magnetic field, and high power density in SPARC will produce reactor-class diverter conditions, and therefore will serve as a test bed to benchmark empirical scalings, computational models, and mitigation strategies suited for fusion power plants. Empirical scalings of the heat flux wise yield lambda equal 0.3 mm mapped to the outer midplane, resulting in a peak unmitigated parallel heat flux of Q bigger than 6 gigawatt per meter square at the SPARC diverter target plates. For the PRD scenario, P equal 29 megawatt. The surface heat flux profiles have been estimated for the inner and outer diverter targets, assuming toroidally symmetric target plates, resulting in 100 megawatt per meter square of peak heat flux for both inner and outer diverters, with an incidence angle of alpha equals 0.95 degree. Tile shaping of eliminate leading edges is estimated to increase the peak values by 50% on account of the desired simplicity for the design and construction of SPARC and the limited overall lifetime. The diverter is being designed to withstand these heat loads without active cooling, without remove handling, and using established PFC materials. A key change is overcoming the lack of maintenance in a radiation environment once nuclear operations have begun, as both sustained DD and DT operations pose a health safety risk, unlike many existing devices, but similar to ITER. SPARC is not planning a multi-campaign deployment or upgrade strategy for its PFCs. The decisions to use tungsten-based materials for the PFCs has recently been made after a careful consideration of trade-offs between low and high Z material operations and associated risk, since many layers of plasma physics and tokamak systems are impacted. Carbon-based PFC materials would be preferred for meeting SPARC's mission goals due to improved manufacturability, reduced eddy current, torques, and increased resistance to damage from thermal transient relative to tungsten. However, the tritium retention and high erosion rates in carbon-based materials do not project well towards a pilot plant and would create a risk for the timely achievement of SPARC's goals within limited tritium inventory. Therefore, SPARC will feature a diverter made of tungsten-based tiles, attributable to the gap between current experiments and SPARC diverter conditions. It is not possible to ensure that SPARC will be able to achieve a detached diverter that is compatible with high core confinement. Therefore, SPARC is being designed under the conservative assumption of moderately dissipative diverter conditions, assuming to 50% of the power leaving the LCFS is removed volumetrically before reaching the diverter. Power sharing fractions assumed will be consistent with single null equilibrium for diverter considerations, with a 60/40 outer per inner split. Even though SPARC is being designed to produce up-down symmetric equilibria, the PRD scenario will leverage the feasibility of the toroidal field and diverter coils to produce a to 1 Hz strike point sweep during the 10-second flat top to spread the heat flux over a large surface area in order to keep diverter tile surface temperatures within limits without active cooling systems. As shown in Figure 3a and b, by doing so, the surface temperature of the PFC spikes locally with each pass of the strike point, but conduction into the bulk material ensures that melt temperatures for tungsten will not be reached, while avoiding melt is possible. Short-term surface temperature exclusions above the recrystallization limit will be encountered in SPARC and are unavoidable during sweeping control failures. High-powered edge localized models (ELMs) and distributions are key challenge during SPARC operations will be to budget for and monitor damage of the tungsten surface over the device's lifetime. The sweep trajectories are being optimized to match the capabilities of the power supply systems. Modeling work with UEDGE and SOLPS ITER is underway to predict diverter and edge conditions and identify impurity seeding and detachment requirements for the high-power scenarios. SPARC will be used to explore potential solutions for achieving and controlling detached diverters at conditions relevant for fusion pilot plants. A dedicated advanced diverter mission, which complements the primary Q bigger than 2 mission, drives device decision and diagnostic requirements. The coil systems and diverter shapes are being designed to study double null long-legged and X-point target XPT diverter configurations, which have been proposed in the design of compact pilot plants due to the wide detachment power window. Also, the XPT scenario will not be able to run at full plasma current, I smaller than 5.7 mA. It is still expected Q bigger than 2 and substantial fusion power. P equals 37 MW, resulting in a unique platform to study advanced diverter scenarios. Figure 3c depicts one possible XPT scenario. In particular, SPARC will explore the effect of the secondary null location on power dissipation, as well as the sensitivity of the detachment location and dissipation to the external controls and transients. Modeling of the XPT configuration with UEDGE is underway, as well as the evaluation of the requirements for X-point position control. Many of the topics addressed by the Advanced Diverter Mission parallel these identified by the fusion community, although there is an emphasizes on obtaining the minimum viable information necessary to inform ARC, which necessarily limits the measurement capabilities. Unmitigated type 1 ELM frequencies of 3 to 15 Hz have been projected, with a peak parallel energy fluence of 11 to 32 megajoule per meter square to the diverter. Similar to eta projections, also surface heat flux laws are presently envisioned to be smaller due to a lower angle of incidence. Estimated diverter ELM thermal loads result in heat flux factors between 3.7 to 39 megajoule per meter square per second half. Over large fractions of the diverter surface, which will allow for exposure from one to a few ELMs to expand the H-mode operation window, increase margin, and ensure survivability of the diverter PFC's extrinsic. ELM mitigation tools are being considered by the SPARC team. The feasibility and requirements for pellet injection, resonant magnetic perturbations, and plasma jogs are currently being evaluated. At the same time, small ELM and intrinsically ELM supports regimes such as I mode and QH mode are also being considered. Also, both extrinsic and intrinsic mitigation techniques often lead to reduced pedestal pressure, given the large margin that the PRD scenario has to the Q bigger than 2 mission. It is expected that SPARC will readily meet its primary mission, even with the reduced confinement associated with lower pedestal performance. The transient loading to the diverter surf from the unmitigated thermal quench of disruptions in PRD scenarios has been estimated to produce heat flux factors of up to 1 to 2 gigajoule per meter square per second half. When uncertainties in physics parameters are propagated, such an event will push any material limits and will cause top surface melting of tungsten. Disruption mitigation will be utilized, but the high power density may still result in main chamber PFCs seeing heat flux factors of severe tens of megajoule per meter square per second half, depending on toroidal and poroidal peaking of the thermal quench. The effect of these high transient thermal loads in the bulk PFC is being assessed through computational modeling and testing of plasma-facing material. Nonetheless, the SPARC team is focusing on disruption mitigation techniques to avoid these problematic situations, as will be described in the next section. Thank you for listening to the end of today's show.